In this video we're going to look at the conjugate points on a parabola. Now we've already derived the equation for our parabolic trajectory in the first course, but we're going to have a look at that again and we're going to find the conjugate points for that particular equation. So let's remind ourselves of the equation we derived in the first course. So if you go into the resources section, you'll see that there's a file there for the graphical calculator Desmos, so you can go ahead and open that up if you like. Now you'll see that there's a folder there called Conjugate Points. This equation here was the equation for our parabolic trajectory that we derived in the first course. So if you're unsure, you can always go back to the first course and check out this derivation. Now if I was to put the curve on, so that's the curve in green, so this is our parabolic trajectory here. Now you'll see that we're going to have the launch angle, so the launch angle is going to be given by the value of alpha, so that's this angle here. So we can see that this equation here, which was derived in the previous course, is indeed an equation of a parabola because it's got a function of x squared whenever we multiply out these brackets. It's also a function of x, and there's also constant terms as well. So it is of the general form ax squared plus bx plus c, which is the equation of a simple parabola. Now we're not actually going to use this equation here in the simulation because this equation doesn't work over the entire domain of our value of alpha. That is, we want it to work from plus 180 degrees to minus 180 degrees, but this function here doesn't work over that entire domain. So what I've done is I've derived another function which is very similar to this function, which allows us to see the parabolic trajectory over the entire domain. Now I haven't got this derived here in this video, but if you're interested, I'll put it in at the back in an appendix section of the notes. So let's get rid of this here and we'll move on to this function here. Now you can see this function is indeed just the same as the green one. Okay, so we are actually got the same function, but it's going to work over a much wider range of angles, which will allow us to see exactly what's happening. So this is our new function here. So let's talk through the angles here that we're going to be using. We've got angle alpha, as I said, is the launch angle. So let's say, for example, we make the launch angle at 0 degrees. So in effect, when the alpha is at 0 degrees, you could think about the cannon as facing parallel with the ground. So the cannonball is just moving in this direction here, parallel to the ground. Now as we increase this angle alpha, you'll see that we're going to fire the cannon at a particular angle and it's going to land at a certain distance. And if we increase this angle, we'll get a point where we will have a maximum distance that we're going to get. So there's a maximum distance here, it's roughly about 0.6 at a particular angle. And then as we increase the angle, then the height of the cannon increases, but the distance that it's going to travel is going to decrease, and we can see that distance decreasing here until eventually, whenever we get down to 90 degrees, then what we're going to do is we're going to be firing the cannon directly into the air, so directly up, and the ball's going to go up and then come straight back down again. And then we can move to the left and we can fire the cannon in the opposite direction. And you can see here that we're going to have the same trajectories, but we're going to have it in the opposite direction until eventually the angle goes to minus 180, which is in this direction, in which case we're firing the cannon in to the left parallel to the ground. So that gives us all of the angles that we're interested from plus to minus 180 degrees, and it models the height and also the distance that the cannonball is going to go in this parabolic curve. So I've changed the values for alpha, our u, and our s to 1, 12.07 and 8.2. It just allows the parabola to fit nicely on the screen. Now we're going to talk about how we can generate this parabola in terms of a focal point and something called a directrix. So if we head into the equations here, what we can do is we can define a point called the focal point. Now this is the focus of this parabola here. And the idea is that we can create a line called a directrix. So this is the line here, which is called the directrix, and this is a point which is called the focus. Now what we do is we map out a locus of points which are an equal distance from the focus to this curve and from the curve to the directrix. Now this locus of points is going to be our parabola. Now that's just lots of words, so let's have a look and we'll see what it actually means in practice. So we're going to have the distance from the focal point up to the curve. So we can put that in here. So let's find the actual curve for that. So that's going to be this distance here. So that's the distance between the focal point and our parabola. And what we're saying is this distance here is going to be the same as the distance from this point here up to this special line which we call the directrix. So this line from here to here, we're going to have this distance. Okay, so it means that this point here, this line from here to here is the same from here to here. So if we were to adjust our points here at S, you can see that what happens is that this length here is always the same as this length here. And the point here that it maps out is our parabola. So we can just adjust that and you can see that moving all the way along the curve. So that's a little bit of revision about how to create a parabolic curve using a focal point and a directrix. Now we're not really interested in this for the moment, it just gives us an indication of what the focal point is and what a directrix is. So let's get rid of these for the moment. We can take these out, we'll take that out and we'll take that out, and we don't need that for the moment. Now what we're interested in is the conjugate points on this curve. So what we mean is this point here is our centre point. This is the point where our cannon sits and we fire the cannonball. So we're looking to find a point that is conjugate to this point on this curve. Now we're not going to prove it here, but we will prove it whenever we do the mathematics at the end of the video. But it turns out that we can find this conjugate point quite simply by drawing a line from this point here up through the focal point, and where this line hits the curve, that will be our conjugate point. So let's put that line in. So this is a line from the origin through the focal point, and it hits the curve at this point here. So this point here is conjugate to this point here. So you can see that if we were to adjust this round about, if I change this one here, the alpha, you can see as we adjust the alpha, then we're going to continually adjust where the conjugate point is in the curve. So when we're down here, the conjugate point is this point here. Okay, so as we adjust this, the conjugate point is going to change. So let's put in the label for this conjugate point. So if we head down to find the focal point is here, and there's a conjugate point here. So we'll put a label in there for the conjugate point. So we know this point here is going to be conjugate to this point here. So remember that alpha is our launch angle. We've talked about that before. The value of u is the initial velocity. So you can see here that the initial velocity is just going to make it smaller, or it's going to make it the whole thing larger. Okay. Now the value of s was just the parameter we used in order to sweep round about the curve. So that was in order to generate the entire curve using our focal point and our directrix. So that just works its way round about the curve. Now the main result of this video is that if we were to keep the initial velocity constant and we were to adjust the launch angle here, then we're going to create a family of different curves. So of course I've only drawn one curve here, but you can see that curve changes. So in effect we could draw out all of the individual curves, and it turns out that the conjugate point here will actually map out the envelope of all of these curves. Now that's best seen by example, so let's go ahead and we'll actually produce about 15 or 20 of these curves, and we'll see that the conjugate point actually follows the envelope of all of these curves. So we'll go ahead and we'll take this point off because it doesn't add any value here. Now we can add in a family of these curves, so I've got a family of the curves here. So let me zoom out a little bit. So all I've done here is generate a certain number, maybe about 10 or 15 individual curves. And you'll see that if we were to move along the family of curves here by changing the launch angle alpha, you'll see that the black curve that we have here just sits on top of the green curves. So you can see it moving along here, and we're firing it in the opposite direction. Now if I was to zoom in at one particular point, so let's say we get it in between here, and I was to zoom in at this point here, you can see that we've got a curve that's actually in between. So we can see then that the conjugate point here, if we were to follow this and we were to put another curve here and also one here, then this conjugate point here would actually map out the locusts of all of the possible parabolas that we would get whenever we were to fire this cannon. And we can see that by actually putting the tangent in to the conjugate point. So let's add that tangent in here. So that's the tangent to the conjugate point. Now I'll zoom out here a little bit, and you'll be able to see as I move it along the launch angle, you'll see that that tangent changes. And you can see it's mapping out this envelope of all of the possible trajectories. So let's just zoom right out here, and you'll see that we have all of the trajectories here. And you can see that that tangent line covers all of the possible trajectories, generating that envelope. So it means, for example, if you were an aeroplane and you were flying past, as long as you're out with this locus of points, then the cannonball won't be able to hit you. But if you fly within this set of curves, then that cannonball could hit you. Now, of course, if we want the cannonball to hit the aeroplane, then what we could do is we could add more gunpowder to the cannon. So in effect, when we add more gunpowder, we would be increasing the initial velocity of it. So this here would increase the initial velocity, and of course it's going to expand the range of the cannonball. And if we were to decrease it, we would decrease the range of the cannon. So in summary, the conjugate point maps out a locus of every possible parabolic trajectory. Now, as in the previous videos, we're going to work through an analytic method of finding what the x coordinates are for each of the conjugate points. So before we do that, let's have a little look at what the answer is actually going to be geometrically. So let's simplify this. We'll get rid of some of the points here. So we can get rid of that, and we can get rid of this here as well. Now what we're going to do is we're going to draw the line, and we'll shift it over so it's at the other side. It just makes it a little bit neater. So we'll put it over to this side here. Now it turns out that in order to find the x coordinate of the conjugate point, so that's the conjugate point, and we're interested to find how far along the x axis the conjugate point is. Now in order to find that geometrically, if we draw a line from through the focal point down to the x axis, so let's head in and see if we can find that line here. So that's a line from through the focal point down onto the x-axis. It's parallel to the y-axis, and we're also going to draw a line from the focal point to the conjugate point here. So again, I've got a little line here somewhere, so it should be x3 y3, so there it is there. So if I click on this here, you'll see we get a little line from this point to this point. Now it turns out that whenever we work through the analytic derivation of the x coordinate of the conjugate point, then the x coordinate of the conjugate point is going to be given by this distance here times this distance here. So that's the distance from the origin to the x coordinate of the focal point, and if we multiply that by the distance from the focal point to the conjugate point, then the multiplication of that is going to be given by a certain quantity. Now the certain quantity turns out to be the value of our c here to the power of 4 all upon the value of g squared. So g is just our gravity. But we'll see that whenever we go through the mathematics next. So let's leave you with the little simulation, and we'll run the simulation, and you can see all of the possible trajectories. Let's look at the analytic method of finding the x coordinates of the conjugate points on our parabola. Now this is the equation of our parabola here. We've got it drawn out here as well. We've got our y coordinate and our x coordinate. We've got our parabolic path here, and we've got a little vector here, and the length of this vector represents the initial velocity of the cannon, which is ball, which is a value of u. Now we know that we can get the x coordinates of our conjugate points by finding the partial y by, in this case here, the constant is going to be c, so partial y by partial c divided by partial y by partial d. Now d is the distance here at which the cannonball lands. And we make that equal to partial y by partial c by partial y by partial d at the value x is equal to 0. So we derived that a few videos ago, and we've used it over the last couple of videos. So let's go ahead and we'll find these partial derivatives of this equation here. So we're wanting to differentiate this thing here with respect to c, and we want to differentiate it with respect to d. Now I haven't added in all of the lines here, so what you can do is you can transpose the 2g underneath here in order to do the differentiation. So I've already done that previously, and these are the equations that you end up with, but by all means go ahead and check them, and if there's any problems you can get in contact. So the partial y by partial c is going to be given as minus 2c plus the g squared x minus d times 2c to the minus 3. So we're just differentiating it with respect to c here in this case. So you can see here in that case then that the x minus d squared is just a constant, and this is equivalent to g squared times c to the minus 2. So we're just going to end up with the 2c to the minus 3, and we've taken the c to the minus 3 down, which just becomes c to the 3. And that simplifies to minus 2c plus 2g squared x minus d all upon c cubed. Now the partial y by partial d is simpler. These disappear now, but it's going to give you, the last term here is going to give us our minus g squared c squared x minus d all squared. Now what we have to do is we've got to divide these out, so it's partial y by partial c divided by partial y by partial d, and that's going to give us this equation here. Okay, so we're just dividing this line here out with this line, which in effect is the same as multiplying by the reciprocal, so this just goes to the bottom line here. So we're left with this equation, and again we can rewrite it in, we've got this equation here, and then what we do is we rewrite the equation, but we do it with x is equal to 0. So we take the x out here, and we're just going to be left with these values here. So we've got this equation. Now this here is going to simplify as well, because what we want to do is rewrite it in terms of our values of x minus d. So when we transpose this in terms of x minus d, we get x minus d times the value of d is equal to c to the 4 upon g squared. Again, I haven't written all of the mathematics out for that, but you can go ahead and just transpose that for yourself. So as we've seen when we looked at the graphical calculator, we're going to have the distance x minus d. So this is going to be, the distance here is x. So x minus d is this small distance. So that's the distance from the x coordinate of the focal point to the conjugate point. That's our x minus d, all times the distance from the origin to the x coordinate of the focal point. So that's the d here. And that's going to equal the value c to the 4 upon g squared. And that's what we mentioned whenever we looked at the graphical version of this. So this allows us to find the x coordinates of all of the conjugate points of a parabolic, a general family of parabolic curves. That's all for this video. Quite long and quite difficult at times, so take your time to work through the mathematics, and if you get any problems, get in contact. Thank you for listening. I'll get you on the next video. Goodbye.